What's going on, guys? I wanted to talk a little bit about what is probably one of the most difficult aspects of machining, and that is boring. There's not many operations that strike fear into the heart of a machinist more than boring does. When you talk about long overhangs with small diameter tools, it can get hairy in a heartbeat. And the main thing with boring that is always at the forefront of every conversation is overhang. That is a projection from the actual holder itself to wherever you're going to be cutting. And as that length increases, the risk of chatter increases. So as you look at different types of boring bars, we have bars here that are heavy metal and carbide and steel. And we've actually got a dampened bar in the back here that we'll talk about later. But every one of these bars has different tendencies and can do more with the same amount of body, basically. So this tool that you see here, while small in diameter, can actually bore as deep as a 1-inch bar, which is pretty incredible when you think about it. But we'll talk about that here in a second. Probably the most important aspect of boring is the length to diameter ratio of a bar. When you're selecting a bar for your project, let's just say that you have a 1¼ inch bore and you have to go in 5 inches deep. That's going to be a tall order for a lot of these bars that you see here. When you're talking about length to diameter ratio, you have heavy metal bars, which you might be able to go up to 6:1 on your length to diameter ratio. So an easy one with easy math would be a 1-inch boring bar. So a 1-inch boring bar with a length to diameter ratio of 3:1 can go 3 inches deep before chatter starts to present itself and you have to start pulling out every tip and trick in the book, which we'll talk about that later too. But when you're sticking out, let's just say 3 inches from your tool holder, you're going to have almost no trouble and be extremely rigid at 3:1. With high-speed steel, you might get out to 4:1, and at that point, you might have to start playing around a little bit with your speeds and feeds, maybe reduce your RPM. And when you get out to 5:1, you'll actually start to notice a difference in quality of the bar, where some steels actually perform better than others, which is hard to believe, but it's true. I've experienced it. When you're talking about say a $25 eBay boring bar versus a couple $100 Sandvik boring bar, you start to really notice it around 5:1. So we'll set this guy down, and then let's talk about the heavy metal bars. This little 3/8 boring bar, I have actually stuck out to a 6:1 ratio and beyond and had good results. So if you look at that, we're talking about a 0.375 times 6. We're talking about boring 2¼ inches deep with this tiny little bar. So that makes this extremely versatile. But why wouldn't you just select a carbide bar or a heavy metal bar every time? Well, that's a good question. And the reason that we don't, perhaps, is a lot of times these are a lot more expensive and they're more delicate. It's easier to break these bars. Say if you're doing a deep bore and the chips pack in as you reach the bottom, it's easy to snap these. So let's talk some more about steel, which is what most of you are probably used to running, and try to maybe convince you on why you should at least invest in one carbide bar. We have a carbide bar here, which is 1/2 inch in diameter. So we know the ratio on carbide is 6:1 with basically problem free, right? So we're taking 0.5 times 6 equals a 3-inch bore depth, which is what we have here basically. And I just ran 30 high-dollar parts with this bar without issue. And I'm actually even just holding it in a collet, which a lot of people might frown upon, but as long as you don't go and use this collet for milling or anything important down the road and you designate it just for holding this tool, this is actually a great way to hold it from my experience. So let's look here. What do we got next? So if you have a project with a 1¼ bore and you're going, say, 5 inches deep, that's a ratio of 5 to 1. Now, technically, you're going to start looking at a bar like this is a, let's just check here. This is a 1-inch bar, right? But then that 1-inch bar actually has a minimum bore diameter of 1.106. So you need a little bit, unless you feed into your hole and then feed straight back out the way you came, you're going to need to retract a small amount. So I would say the functional minimum bore of this bar is about 1.15 inch. So if we know that this bar is only trouble-free out to a 3 to 1 ratio or 3 inches deep, and we need to go 5 inches, I can tell you right now we're going to be struggling. We're going to be pulling out every trick in the book, and unless you're a seasoned machinist, you're going to have some real trouble with this. So what can you do? You could look at something, and what I would recommend if you're just looking for a bar that you're going to be trouble-free with, I don't actually have one here, they're all tied up at the moment, but something like a 3/4 inch carbide boring bar, you're going to be able to go 0.75 times 6, about 4.5 inches trouble-free. Now that carbide bar, if you start, say, reducing the RPM or just employing minor tips and tricks to get that boring bar to do what you want, you're going to get that 5 inches easily with a 3/4 bar, which isn't a huge investment. And we'll talk about inserts later because that's going to make a tremendous difference as well. Depth of cut, all kinds of things play a huge role in your results when boring. So we know right now we're looking for a tool. What do we have here that can do this? There's only one bar on this table that can do that trouble-free, and that's a dampened boring bar. So we got 3 to 1 with the high-speed steel bars. We got 6 to 1 on the carbide bars and the heavy metal. This is actually a tiny little boring bar, but this is one of my favorite guys. This is from Thin Bit, and I've done a lot of small work with this one and a lot of work with this. This one's actually from Maritool. This is the 1/2 inch carbide. They have good value tools actually. Their carbide bar, I highly recommend it. This is a coolant through one. So the reason that these carbide bars work so well is that they're a lot stiffer than a steel bar. So why stiffer's better? Why is the next bar I'm going to show you so good? The next bar I'm going to show you basically takes that chatter wave, and if you're looking at that bar and as soon as it contacts the material, you see it start going like this, which it would if you were to look at it under high-speed footage. That chatter, it would actually be hopping along like this out at the tip of your bar. A dampened boring bar will actually work with that to go and hit basically the middle of that chatter wave and deaden it out. Where carbide just relies on stiffness to not go up and down, whereas steel, unless you're short enough and rigid, you're not going to have that dynamic stiffness. So steel good, carbide better, dampened best. And then there's actually dampened carbide, and they're a little bit of money too. But these here, this 1-inch boring bar can go up to 10 inches deep without any trouble. It's basically set it and forget it. This has actually interchangeable heads, so you can actually remove these set screws and you could put a threading head on here, or you could put a grooving head on. You see we've got lots of different grooving tools here. If you look, they have a good selection. Sandvik is pretty much my go-to, and trust me, this video is not sponsored by Sandvik, but after years of doing this and struggling and figuring things out the hard way, you don't mess around with tooling, and Sandvik I can 100% endorse as the no mess around solution, at least for me. Especially with inserts. I might not necessarily buy a tool from Sandvik if it's unbelievably expensive, which a lot of times it is, and that's just being honest with you guys. A lot of this tooling, say you need a boring bar, Maritool is going to have a good value bar for you, but I'm not necessarily going to buy inserts from Maritool. I might go to Sandvik for my insert and buy the cheaper steel from Maritool. So here we're looking at basically the dream setup when you're talking about steel. when you have a large hole where all you can do is select your biggest bar, you can select a fat guy like this 1.5 inches and run it in there nice and short, rigid. That's kind of the dream scenario. You're going in there with a cheap tool and getting the job done. And if you're encountering situations where you need a tool like this dampened one often, it is going to pay dividends to go out. When you have a job or many jobs that keep coming up and you keep needing to bore deeper holes and achieve that good surface finish, you are really doing yourself a disservice by not investing in something like a dampened tool. It took us a while to really feel like shelling out. I think this whole setup here is around $3,200, which is an extreme amount of money for a boring bar. But when you think about what it can do things that no other bar on this table, no other bar really in existence can do. People all throughout the 50s, 60s, 70s, they would have loved to have a tool like this and this kind of technology. And it is worth every penny if you need one. It's going to be something where maybe you don't start there, but if you keep encountering that, just like everything in this trade, if you need it and don't buy it, you'll have paid for it and not have it. Think about that. I believe that's a quote from Henry Ford, and it's so true with machining. If you need a tool and you do not buy it, you will definitely have paid for it. Something like this, if you have a job where, say, you could have got in and put the bar in and got all your work done in a couple of minutes instead of fighting all day with a job, think about your job shop rate. Times that by 8 hours your shift and think about how much money you're losing every time that you go and you beat your head against the wall not investing in the right tooling. And that's with everything. And that's one of the things you really need to know about this trade is it's not going to be cheap. You're going to have to spend to make money, basically, and you need to develop the skills to back it up as you go. And it's one of those things where you can be handed every tool under the sun, and unless you know what you're doing, you're not going to get your money out of it. And we're here to hopefully help you with that. Let's go to the machine and I will show you what I'm talking about when I say that this 1-inch bar here can only stick out this far without chatter, yet this 1-inch bar over here can stick out 10 inches. I've only got this pulled out 9 inches. I have room to spare, and you can even go beyond that 10 ratio once you start playing around with all the tips and tricks I'm going to share with you in a second here. Set this guy down carefully. Costs as much as, well, it's a lot more than my first car, I think, to put it into perspective. Alright, let's head over to the machine. Alright, so let's get this started off with a steel bar. This is going to be your typical setup, and we've got a 1-inch bar here. So, like I said earlier, your ratio that you can stick out without chatter is going to be 3:1. So we've got a 3-inch projection here, 1-inch bar, and we'll just tighten this down a little bit. And we'll do a little bit of what's called the knock test. If it sounds good in the setup, it's probably going to cut okay. So if you listen to how this sounds, you hear how that sounds nice and rigid. I'll have to stick it out further to really show you what it's like once we get to 4:1 and 5:1, and you'll start to hear that tone become higher pitched, which is the same thing that you'll hear when you're chattering. Basically, chatter is not your friend on basically every machining operation that you do. It's going to be a constant foe in your machining career, and the sooner you accept it and learn how to deal with it, the better. So here we're at 4:1. A little bit higher pitched, right? Let's try 5:1. It's getting a little difficult here because I've got a high pressure coolant line plumbed directly into this block that's kind of fighting me here. See, it's wanting to pull it back. Let's go out as far as this will let us go. There, we are at 5:1. I could get another bar on there and show you, but you get the idea. At this point, it's going to start sounding real bad as you start machining. Ooh, you hear that high-pitched note? Very high chance of chatter at this point without basically every trick in the book on high-speed steel bar. So we'll let that guy back in, get him out of our way, and we'll carry on. Let's listen to the Sandvik bar, but first, something of note, I think I just knocked the camera, sorry about that, is one of the tips and tricks for boring is to actually split your holder. So these blocks from Haas actually came with set screws, and those set screws, the 4 points of contact as you tighten them against the bar is not nearly as firm as a hole as imagine holding onto the bar with your hand, right? If you pinch something with your fingers, how well can you keep something from ripping it out of your hand? Not very well at all, right? But if you really have a hold of something, all of that surface area aids in the same way that it does with a boring bar. It's going to dampen vibrations, give you a better hold. Overall, it's superior. So what I did was I actually split this block, and then I used the screws that are actually going into the turret from the direction here, and you see with the split, I just used a cutoff wheel and cut that right down the line very carefully. And as you tighten these down, there is a such thing as too tight when you're talking about the plastic deformation of this entire block. If you over tighten these, even at a 3-to-1 ratio, if I was to really pull down on these, you will actually hear chatter all the way down here at 3-to-1 because you have actually plastically deformed this round block and made it oblong, and you'll actually have areas of contact and no contact. So definitely if you split your blocks like I recommend you doing, don't over tighten them. Do you hear that? That's a beautiful sound. When you have a projection on a 1-inch tool that sounds like that, you can't beat it. It's going to be rigid throughout its range, even if we were to use the rest of this bar and stick it out even further. When you're working with a pretty good length to diameter ratio, and a lot of times what you're trying to do is avoid chips packing in the bottom of the bore, as you have a tool that's almost the same diameter as your bore, all those chips are being pushed ahead, and there's nowhere for them to go. Unless you can break a chip, which is sometimes hard to do depending on the material and your insert choice, which I'm going to help you out with in a little bit here, it can be very hard to break chips up fine enough. And you see I make pretty fine chips around here. That's really one of our calling cards, is chip control, so that you can get that production going. I just threw chips down my shirt. Fun. You want to go with a smaller tool as long as it's still rigid. But if you listen to this bar here, you hear how good that sounds? That's sticking out 3 1/8 inch, which is a long ways for a 1/2 inch tool. But like I said, you should be able to get this tool to run almost as good as you can with the 1-inch bar. Now you're not going to be able to maybe take as big a depth of cuts because your insert is only so large, right? Normally you take up to about 60% of the insert. So on this tool here, a lot of times I don't really exceed 80 thousandths on this little guy just because I don't want to break him. But on the 1-inch tool, as long as you're within that 3-to-1, 4-to-1 range, you can take pretty much 80% of the insert if you're so inclined. With the dampened bar, you can do the same, but for the price of these, I really don't push them too hard. Most of the time, I stay conservative and really use it for getting that fine finish without having to go in there and mess around like reaming a bore or polishing. All of that takes way too much time. Now here's something neat. I'm actually on our website here. If you go to education and you go to boring tips and tricks, we've got a bunch of different educational articles on there, but you should really check it out. If you're watching this video, you should definitely check it out. But I go through and I talk about all these things that we're discussing in this video, but down at the bottom here I have, let's see, 13 tips and tricks. There's a lot more, but these are your main go-tos when you start experiencing chatter. So, number 1, reduce cutting speed. That's almost always going to be your number one thing If everything's set right with your tool and you know in your heart that there's nothing more you can do with the tools you have to work with, you got to start employing some of that machinist black magic. So reducing your RPM is number one thing you want to go to almost every time. So let's just say that under ideal conditions you would be at, on stainless steel, 400 surface foot. 400 to 600, we usually run in that range. And then as soon as you start hitting chatter, the first thing I'm going to do, maybe I'll drop it down to 200. Does it go away? No. Okay, we got serious problems here. If you're down at 200 SFM and you've cut your speed in half, you're going to start having to pull out some more stops. So the first thing you want to do after reducing your speed is look at something like this Haas is capable of spindle speed variation. Let me see if the spindle's in the shot here. So basically, if your spindle's going at whatever diameter you're cutting, 1500 RPM, you can actually go into the control and you can tell it to modulate that RPM from 1500 to 1400 back up to 1600, and you can specify how long it takes to get in between each range in down to the millisecond. So that spindle will actually ramp down and up, down, up, down, up, down, and that disruption of the pattern of the RPM can actively counteract that wavelength and break up that chatter, which is really amazing. And if you have spindle speed variation on your machine or something like it, you should really check it out. It's really powerful. So that's probably where I would go for number 2, is I'd immediately try spindle speed variation in combination with lowering my SFM, my speed. Now, one of the fundamentals you really need to learn about boring is it's do as I say, not as I do. When you're talking about your depth of cut, you need to have a significant enough depth of cut for your conditions. And what I mean is, if your depth of cut is too light, you can run into extreme chatter simply because there's not enough pressure and loading on the tool, pulling on that tool to actually prevent it from bouncing up and down. So say you're trying to take a mirror finish or a whisper pass and you're like, oh man, it sounded great when I was taking 30 or 50 thousandths or 100 thousandths depth of cut, and then all of a sudden I go in and I try to take a 10 thousandths depth of cut and it's chatter city. Well, you've got to play around with your depths of cut leading up to that finish pass, and maybe try one of those whisper passes beforehand to know what you're getting yourself into, because you can run into major problems where you did not have a big enough depth of cut on your finish pass, or maybe you left too much material. And that's something that you need to know your part, you need to know your machine, you need to know your setup. It's an experience thing, but basic rule of thumb is you want to take at least the corner radius on your insert. Let me grab an insert here. Put my phone in my pocket a second. When you're talking about the corner radius, it's the actual radius on the tip of your insert. This particular insert is a 1/32 or 0.0135 corner radius. So if you're not taking a depth of cut of at least 0.0315, there's a good chance you're going to run into some issues. I'm not saying you have to, but you're going to activate your chip breaker and you're going to get a lot more favorable conditions 9 times out of 10 if you're taking at least your corner radius for depth of cut. Now, that can be a sticking point on small lathes that don't have the horsepower, and in that situation you might want to go to a different style insert or a finishing insert. All these inserts are not created equal. You need to get that out of your head early on in your career as a machinist, is that every insert does a different thing. So here we have a 0.015 corner radius on this insert. This is actually my go-to insert for finishing steel. Leaves an extremely nice finish without any fuss 9 times out of 10. This is a great insert, and all these are available on our website under the education tab. We don't get any sort of kickback from Sandvik or anything like that. We're just sharing what works for us. But a smaller corner radius, like I said, with needing to take at least your insert for your depth of cut, if you reduce your corner radius size, your insert, choose wisely, you can get away from some of those issues of needing to take such a large depth of cut for a finished pass. You can get down to an 0.08 quarter radius is a lot better than 15 when you're finishing if you need it. As your corner radius decreases though, a smaller corner radius is going to generally be a less durable insert. This insert's going to wear much faster than a 1/32 .031 insert would. And that's something you always got to keep in mind. I'll try to get a close-up of some of them inserts then to show you what I'm talking about with the different chip breakers. But increased depth of cut, increased feed rate. So that's going to be a major one with surface finish. So you have this balance of needing to feed hard enough to break a chip and also feed hard enough to load the tool. That's all part of loading that tool, just like depth of cut is. But if you are feeding too hard, obviously you're going to have not as good a finish as if you reduce your feed rate. So that's one that you're only going to use when you're roughing, basically. Unless you use something like a wiper insert, but that's a topic for another time. Choose a smaller tool nose radius, we covered that. Minimize the bar stick out, yes. Always reduce your tool to the minimum length you need, even if your tool can run at 3:1 rigid, unless you're trying to set it and forget it. If you're really trying to get work done, get it as short and rigid as possible. We've talked about spindle speed variation. Grip the bar by at least 4 times the diameter. So that's an important one. When we were talking about this 1-inch bar, you see this holder is about 3.5 inches wide, so it's really ideal for this 1-inch bar. You want to hang on to at least 25% of the bar in a perfect world if possible, but 4 times the diameter is a good rule of thumb. Use cylindrical clamping, we've talked about that. Choose the largest bar possible, we've talked about that. If you have a 1.5 inch bore and all you have is access to high-speed steel bars, you're not going to want to use a little steel bar that's only 3/8 in diameter. You're probably going to want to use a 1.25 bar or 1 3/8 bar if you have one. Reduce the feed rate if it helps. So a lot of times increasing feed rate is going to help to an extent. Maybe you need to back it down, you're going a little too aggressive. Use coolant, that's a good one. Just the addition of coolant can sometimes dynamically affect the boring process to where just that added lubricity or chip evacuation, all of a sudden your chatter's gone. One of the other neat ones too that you may have encountered in your career is you find that a brand new fresh insert is all of a sudden chattering when the one that was a little worn sounded great. What the heck, right? We've all been there too. Sometimes you need to just maybe dull the tool just a little bit, use it in the cut for roughing, for maybe just a pass or two, just to take that sharp edge off, or maybe there's a micro burr that you would only see under a microscope, and all of a sudden you've got another good finishing insert for what you're doing. Alright, where were we here? Proper alignment. This is going to be a major one. Turn the machine on here a second. Make sure we're not going to run that big bar into the chuck. Let's swing that down here. What is that? T3 maybe? Nope. Oh, I typed in 13. T3. Okay, where were we? So when you're talking about a bar like this round bar has no features to orient off of. So normally you would grab something like you would grab a square or a series of squares. So an easy way to actually set your alignment on your tools, I have a coolant line back here, but picture that wasn't there. You can actually just go on the flats of your bar up against the face of your turret, and as long as your turret is in proper alignment, oftentimes that's enough, just going from this surface to this surface on the face. And another neat way is to put an indicator onto the flats, and you can actually just jog up and down in your axis, and when that reads dead needle, right, no movement up and down off of the x-axis or whatever axis your machine is aligned to, tighten it down and you should be good to go. Generally this insert tip should be in a correct orientation when this flat is in the right position. You can bring your tailstock point up, and as long as your tailstock's on center, you can use it to align the point on your tool. That's another good one. I got dozens of different ways of setting your tools on center. Sandvik actually makes a little level that when you pull this head off, it seats onto the front here in the little serrations that they have on this, and that's another neat one, but I have so many tricks for it, I didn't find that necessary for us, but definitely if you're looking to save some time on a tool with no reference features like this round one, that's a good way to go. And then finally, let's look here, what do I got? Number 13, work holding of the piece itself. Wow, that's a big one. Let's move the camera over here a second. When you're actually talking about the work holding, so normally you have your part sticking in front of your jaws, right? It can be however long the capacity of your machine is. You've always got to remember what's going on behind your chuck. Do you have a second chuck holding your material back there? Most cases, no. That material is doing whatever it wants to behind the chuck. It's whipping, it's carrying on. Even if you have a spindle liner, unless it's running perfectly true and there's no vibrations, it's going to affect it. As your part changes length and you keep cutting more and more and more parts off, boom, 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 and now all of a sudden you have a 12-inch long piece. That 12-inch long piece that comes out of your last little bit of spindle liner now behaves incredibly different than your piece did when it was 48 inches long. And that's something you always have to consider, is the work holding itself. You want to be holding on to at least 25% of your workpiece diameter as well, just like with your boring bar. And all these things come into play in combination. Alright guys, thanks for watching, and if you made it this far, hopefully you like, share, and subscribe to our channel, and if you have questions, feel free to contact us anytime. Have a good one.